And that one application is just going to be projectile motion. So we're going to have a set formula or set pair of equations, right, for our parametric equations that will help us track the path of an object. So this idea of projectile motion has a really nice connection to physics. It helps you trace the path of an object, but being a little more exact and knowing exactly when that object is at any point on its journey. So if you want to know at what point in time does my object reach its highest point, you can find that out using projectile motion with parametric equations. But we need a set of equations. So I'm going to write down the equations, and then we'll take a minute and define all of the variables that you're going to see. So our two equations will be this. X equals, we say that as v sub 0. It's v with a subscript of 0. T cosine of theta. That is our x portion of our parametric equations. And then our y portion is y equals h plus v sub 0 t sine of theta minus 4.9 t squared. And I want to talk about what all of those different variables mean in our equation. So first of all, v sub 0. Let's define that. This is your initial velocity. In other words, it's measuring how fast is that object traveling at the moment that it's launched, or the moment that you throw the object, or the moment that it's hit or kicked or whatever. How fast is that object traveling? That's what our measurement is for v sub 0. Theta is the launch angle, right? So at what angle is that object being launched? Shallow, steep, somewhere in between. And then h is the launch height. So how high off the ground is that object when it is thrown, kicked, hit, launched, whatever. And then finally, I kind of like to talk about this little guy right here. So this is measuring the effect of gravity, right? Because we need to know, we aren't living in space here. If we launch something, it's going to be pulled back down to the earth because of gravity. This measures your effect of gravity in meters per second. So this measure, or whatever your unit of measures there, measures the effect of gravity. And this is in meters. So if we wanted to change our measurement to feet, we'd have to change our formula to reflect the difference in that number. Your homework is going to be in feet, and I give you the formula in the homework, so it's not a big deal. The only thing that changes is it's just 16 instead of 4.9. All right, so we've got our formulas, I guess, the two parts to our formula. I want to just take one example and just practice using this formula. Okay, so for our first example, let's just say I give you the two of the measurements. First of all, we're going to say h is 0. So our initial height is 0. V sub 0, our velocity at launch, is 26 meters per second. And theta equals 60 degrees. I just want to see, what does the path of that object look like? And I have a few questions I want to ask about that. So the first question is, what does the path look like? And we're going to use Desmos for this. All right, and our second question what is the highest point and when is it there? So what is the highest point of this object? How high off the ground does it actually get? And when does it get there? That's what parametric equations do for us. They give us the ability to measure time as well as distance. And then finally, the third question we're going to answer here is, there's a lot of ways I can word this. So I can say how far did the object travel? What's the lateral distance? What's the horizontal distance? There's a lot of different ways to word this question. I'm going to just say, what is the horizontal distance traveled and how long is it in the air? So these are the three questions that we're going to ask. And we are going to use Desmos to answer all of these questions. Okay, I'm not expecting you to do any kind of fancy calculations here. We're not solving for t. We are literally going to write the equations, type them into Desmos, and analyze the graph of that function. So let's start with writing the equations, because that's going to be the most important thing. We can't do anything if we don't have the equations. So let's write our two equations. So x equals, we're going to use the velocity, which I said was 26 meters per second. So 26 is our v sub 0. T is what has to remain in your function. That is what controls time. I don't know time. Time changes. So we just write t. And then cosine of our launch angle theta, which we said was 60. That's our x portion of our graph. And then the y portion of the graph is, I said the height was 0. The initial height was 0, right? So it's 0 plus something. I don't need to write the 0 plus portion of that. So I'm just going to go straight to v sub 0, which was 26, t, sine of 60, and then minus the effect of gravity, so 4.9 t squared. So what that is saying, for every second squared, the object is being pulled down at a rate of 4.9 meters per second. That's what that object is saying. So as it's being pushed up into the air with its velocity, it's also being pulled back down to the earth by the effect of gravity. Okay, so we've got the equations. Let's use Desmos to actually graph them, and then let's take a look at the graph. So here's what our picture looks like. Let me put this back up on the screen for you guys. It looks something like this. Let me try and zoom in a little bit. Nope, it's not letting me zoom in. We'll just do this. So we have, for sure we can kind of estimate some measurements from this. It looks like it gets about 60 feet that it travels. Really close to about 60 feet along the horizontal axis that it travels. It looks pretty close to 30 feet is its halfway point. And I would say, I think these are counting by twos. So this highest point right here, probably around 26 feet. Okay, so maybe it's about 26 feet. We don't know for sure. We're going to play around on Desmos a little bit more. So on Desmos, I want to zoom in on the place that I'm trying to figure out total distance traveled or height, and then mess around with the seconds to figure out how long it actually takes to get there. So I'm going to change the t value to figure out what's the actual length of time that we're seeing it's in the air. We'd say about, well, first of all, how high does it get? So for question B, question A, we have Desmos to look at, right? For question B, we said, what's the height? Estimating, we're saying about 25.8, 25.9 meters. Somewhere in there. Again, using our picture to help with that. Now we want to figure out the number of seconds it takes to get there. So again, go to Desmos, change your seconds until you get the graph to stop at its highest point. So mess around with your seconds until you find where that highest point is. Once you kind of play around with your seconds, you'll come to see that it ends up being about 2.3 seconds that we're at our highest point. And it just takes some guessing and checking. There's nothing that I'm going to look at in the formula that's going to tell me that. I just have to play around on the graph. All right, and then C, we're going to figure out what is the horizontal distance traveled and how long is it in the air. So looking at the graph, just at our first glance, it looks like it traveled about 60 meters. Let's try to get maybe a little bit of a better estimation by zooming in on Desmos. So after we zoom in, we can get an estimation of, it's about 59, I'm sorry, meters, I keep saying feet, is its horizontal distance traveled. So really, 59.8, is that what I said? Not 5. Yeah. Okay, it wasn't 5. Zooming way in got us a little bit closer than that. So about 59.8 meters. Okay, it doesn't have to be perfect, but somewhere along those lines. And then we want to know what our seconds are. How long does it take to get there? Now, you have kind of a place to start. We know that it reaches the highest point, which is the halfway point of its path, at about 2.3 seconds. So theoretically, it should hit the ground 2.3 seconds after that. So about 4.6 seconds, but let's check. So because we're kind of estimating here, we know it's between 4.9 and 4.6 seconds. Either one of those is a good estimation, but I'll just go ahead and put 4.6 seconds, since that kind of goes along with what we answered in the previous question. Now, I know, for those of you here in class, you can sort of make a little sketch here of your path. I'm going to do that just because I want to make sure I label on here what I found. So this point right here was our question to point B, or to question B, right? That was our highest point. We looked for how high is that highest point and what was the number of seconds it took to get there. So you look for your Y value and your T value at that point. And then here was how we answered question C. Okay, what's the horizontal distance traveled? What's the X value at point C? And how long does it take to get there? How many seconds? So mess around with T to figure that out. All right, so let's try applying this to an actual situation. So we talked about, this is just kind of in a vacuum. We're looking at just some random values that I gave you. This wasn't attached to any situation. But let's look at a situation. All right, so here's our situation. We're watching a baseball game, and nowadays you have all of this data can be measured in real time. Like if you've ever watched a baseball game, they can give you how fast the pitch was in real time. So they can give you a lot of this data. I don't know that they do, but they could. And you could figure out, if you're quick, if it's going to be a home run before they actually hit it. Or not before, but after they actually hit it. This is more really for you to think about if you're going up to bat and you want to hit a home run, thinking about like how you have to hit the ball so that it clears the fence. You know, do you have to hit it at a certain angle? And you learn those things when you're in baseball, like how to hit the ball so it travels differently. Anyway, this is our situation. The first thing I'm going to do is try to graph at least something on Desmos that gives me where the center field fence is and the distance from home plate. So I have sort of a target. And you can do that on Desmos pretty easily. Actually, write the equations. So our two equations will be x equals. Okay, what is my initial velocity? So looking at your,
41 meters.
Yep. So this is your V0, V sub 0. So 41 t times the cosine, and then my launch angle is here, 15 degrees. That's the x equals. The y equals, do I have an initial height?
No.
Right. He's not golfing, right? He's not hitting the ball when it's on the ground. He's hitting the ball when it's up here. So 1 meter above the ground, that's going to be my height. So 1 plus, and then we have our 41 meters per second as our velocity, times t, times the sine of 15 degrees, and then minus your gravity, so minus 4.9 t squared. So these two things together are going to trace out the path of our object, and they're going to give us the information about when that object is at different points along the path. So let's take a look at, so if we look at the picture, again, looking at this picture, we can see that if the fence is out there at 124.4 meters, it hits the ground at like maybe 90 meters from home plate. So this guy doesn't end up being a home run. So is it a home run? For our first answer, we would say not a home run. But what if I make one small change? Just one. Okay, and I'm not even going to change the velocity. What if we just change the launch angle? And we're going to change it to 25 degrees. Okay, and I want to see if that's a home run. Now, the nice thing about these graphs is that you can really just make that change pretty easily and see very quickly if it's going to give you the desired result. So let's take a look at Desmos and see what happens. On our picture now, if we changed it to 25 degrees, we can see that it does in fact clear the fence. All right, so we have, yes, it's going to be a home run. So for this one, if we just make that one change, yep, it's a home run. Okay, it cleared the fence, so it's going to be a home run. Now, if you're a baseball player, you could use this information to practice a little bit hitting that angle, knowing the dimensions of the fields that you're going to be playing at, especially because baseball teams play a lot of games in the same field as you move through the year. They usually have a series of games that they play against other teams. So, knowing that field and knowing the only change you had to make was not how hard you hit it or how high above the ground you hit it, but the angle at which you hit it. So you want to dig a little bit deeper down here than being a little more shallow, and that can affect the trajectory of the ball. A small change like 10 degrees was all we needed to be able to hit that home run. Okay, so tonight when you do this, there's going to be questions similar to this. It looks like it's a lot of questions, but it's just asking pieces. So you're going to answer little pieces along the way. You do have to use the feet formula, which is in the homework, so you can access that right from the homework. The only thing that changes, instead of 4.9, it's 16. Other than that, it's the same exact formula. When it asks you to graph, I'm okay with you just using the Desmos graphs and just copy and pasting them into, taking a screenshot of Desmos and putting it into your Go Formative. I don't need you to worry about sketching the graphs. That's not that important to me.